Welcome to all of you to this webinar on the casting topic. With me, I have the market strategy and the biz dev expert from our team, Padri. Padri, can you say
Yes.
hi, hello, so that we can hear you? Okay,
Hello everyone.
perfect. There's just a few things. If you're not able to connect, or if you have some issues with the connection or the audio or something, please send me a message. Same goes for the questions. If you have any questions during the webinar, we'll keep some time in the end where we can do the Q&A. And I think that's about it, Padri. Any other thing that you want to fill in before we start?
No, I'm good. Thank you.
Okay, then over to you, Badri. I'm going to be muted, so but around. So if you, yeah.
Sure. Thanks a lot, Majid. So good morning, good afternoon, good evening from wherever you are joining. Welcome to this webinar. So thanks for taking time out of your busy schedules. So Majid already introduced me. So I'm part of the market strategy and business team of ESI Casting Solutions, which is Procast, by the way. So the Casting Solutions is part of ESI Smart Virtual Manufacturing, which basically helps to ramp up production by accelerating the virtual development and validates key manufacturing and joining processes to fabricate complex, lightweight components with the highest possible quality. So the topic of today's webinar is technological advancements in simulation to control and achieve high and top quality castings. So the presentation will itself be about 30 minutes, and I guess we will have a few more minutes later on to speak about to have your questions. Okay, so today's agenda, we start briefly with the industry trends and take it down, how it cascades down into the casting industry. So these industry challenges are then addressed via simulation to understand the benefits. Finally, the summary and Q&A. So over to the industry trends now. So the future of mobility. I mean, this is one of the most talked about trend. So which is towards electric, autonomous, connected, and shared. So what does this really mean for the casting industry? So it will definitely have an important influence on the automotive castings from capacity to materials and even production processes. So firstly, let's talk, to go through these points, so let's talk about the combustion engine. So as the combustion engine gets replaced by the batteries and electric motors, many of the different parts of the car become obsolete. So especially, let's say the powertrain castings, as an electric car doesn't have an engine, exhaust pipe, transmission shaft, or even a gearbox. However, the electric car will need electric motor, the battery units, and the reducers. So what does this mean for let's say the foundries? So there will be new castings such as housings for electric compressor or electric motor, the battery unit or the electric motor controller, and the battery charger. So this means that we will have new castings, which is going to mean also new challenges for the industry. So the second point is related to the casting materials itself. So the casting material will have really major change. And the reason for this is the battery units are heavy, which makes the drive system of the electric car heavier and the engine heavier than the engine of the traditional car. So lighter the material, much more the better. So what does this mean? The only light material, let's say, which is also easy to handle is aluminum. So this means that more and more light aluminum will be preferred. Example for these housings, which we already spoke about. So therefore, the shift also from iron to aluminum will continue through these years. And finally, the overall casting weight of the electric car itself is expected to be 30% less than the traditional car. And this is going to pose a threat, or at least expected to pose a threat for the total weight of the automotive castings output during these years as the traditional car eventually fades away from the market. However, what is also to be considered is that the EV today is only a small fraction of the market, and it will take many years to replace the combustion engine completely. So till this transition will happen, the transition will also happen in stages. So for example, we will not move in one day to the EV. So there will also be a moment where there will still be hybrid vehicles, which will have both combustion engine on the batteries. So the automotive casting production for the moment, as predicted, is going to be on the upswing mode for the next years. So Innovation is definitely the key as the automotive casting market gets disrupted. So foundries which need to prepare for this future should be more open for innovation to strengthen their market position. So electrification of this car market is therefore very important for all of us, for the foundry industry, and this is where we need to take through the industry trends and move on to what happens during the day-to-day life of a foundry man. So these, in fact, cascade down to simply the stringent market requirements. The market sets these requirements. So this means that there will be new or complex designs that needs to be cast. So there is always an importance on process control as usual. So to achieve parts with very high integrity, also with parts performing better with good mechanical properties, and of course, because we are talking about the die castings, to have a very good tool life, which is going to last long. So finally, a foundry should be able to predict problems and solutions to them in advance. So also to be able to deliver castings on time, so to be quick to the market, and of course in the process improve productivity and profitability. Okay, so over to the benefits. So over here we have tried to prepare slightly differently, thinking in terms of a designer of how he would like to how he would like to start or how he would like to move ahead. So one aspect, or the first aspect, like what a designer would like to look out for as soon as he receives the part, or even let's say a company would like to look out for as soon as they receive a part to manufacture, is how good is this design made for manufacturing. Okay, we could call it as a manufacturability check, or we could also call it as a castability check. Of course, it also depends on what stage the product development we are in, if there is a possibility to in fact make a feedback to the product designers or not. So if it's a part to be produced by the foundry and the part design owned by someone else, it's probably too late for any modifications. So however, this step certainly helps to understand the risks during the production and could possibly also help to factor in these costs during the coating process. So what are the main goals of such a simulation? Let's say is to be able to understand what is the ideal ingate position, even validate the ingate dimensions, look for a good flow balancing between these runners, to have uh, to have the right flow length so that we are not losing temperatures during the cavity filling, to be able to predict air entrainment, and of course to also predict the last filling regions, which is going to determine the positioning of the overflows. And finally, of course, the hotspots and the potential porosity locations, which is after, let's say, the filling and certification. So as an example, what you see here is it's an example from Renault, so which is coming from its Zoe car, which is an electric car indeed. So, and in fact, this is what you see over here is a gearbox housing. And in this study, actually, there are no dies. So what is done over here is just to select a possible good ingate location, try to fill the part, try to understand all the possible things which we would like to analyze, and then finally look for the last filling region. So we see that there are some last filling regions on the other side of the cavity, so which of course needs to be vented well or placed overflows, and we also see something which is very close to the ingate, which also needs attention. So basically, what is the takeaway is we are able to understand the ingate positioning and the last filling regions from such an analysis quite quick to make it. It's almost a few minutes to make this one. So the second part of this is we allow it to solidify, so which is to predict the hotspots and the shrinkage porosity. And over here, of course, because we don't have the die, there is no die temperatures taken into account. There is no real cooling system also taken into account. So there will be a mass shrinkage, what you will notice in such a simulation. So it is important to understand what is also the quality requirement of the part. And this is what you see over here. So the quality requirement of the part. And it says that this is the critical region. This critical region needs to have no porosity, or to have a porosity under a certain limit so that it's getting accepted, and that is what one needs to do on an analysis already at this stage. So what is found is that this boss and rib network region. So this is what you see. So you see several bosses over here. You also see that they are connected with the ribs. So these are quite thick. So which means that this is not going to be an easy case to handle. So what is already noticed is when we try to analyze over here, what is understood is that the cooling system will have almost no influence, or let's say low influence over here on the porosity. Okay, and then what does this mean is that this already indicates that probably the product design change will certainly help it to be manufactured better. So now it's a stage. If we are at a stage when we have a chance to modify the product design or give feedback for the product designers to be able to modify this one, so that we are able to see some good certification pattern. So this could be one choice. The other choice, as I mentioned before, it is really to factor in these challenges in the coating process, so we know that what are the challenges which will come up during the design during the die design stage. So let's say this was the first step. The second step, usually when we go into go through the next step, is basically to be able to design runners and to be able to validate them with the right overflow locations. And for this reason, what is very important to be able to really go for the full injection cycle, which is from the furnace to the final casting. Of course, between these, one can have a certain step, which is to be able to put the overflows, to understand if the overflows with the ingates, which was ingate locations which was provided before, could be done. So this step I'm skipping. I'm trying to just go one step ahead, which is to go really for the full injection cycle, starting from the furnace to the final casting. So over here, there are again several things to predict. So we have the air entrainment during the dosing. So we can also optimize the slow shot, determine the right switching point, run a balancing, overflow positioning, and the vent positioning. What is also quite important during this stage is the counter pressure influence of the air or the gas inside the cavity. And of course, there could be some heat loss, so which means that we could have potential misruns if the heat is not managed well. So these are let's say the common suspects, which most of you probably know. In this webinar, of course, the idea is not to go through all these ones, but to focus only on, let's say, the aspect of the filling which is related to the counter pressure influence. So as an example over here, what is taken to understand better is that what happens to the gas that needs to be evacuated while having the same machine on the same dies, but different short leaves. This can quite happen simply because you can manage your sleeve length based on what is required, and sleeve length is the fill ratio is dependent in fact on this sleeve length. So here is an example. What you see here, so the first short sleeve, it has a piston diameter of 120 millimeter. It has a short sleeve length of 405 millimeter, and then let's say we compute what is the gas to be evacuated. So this is about 3.4 liter. Now we go to the second short sleeve. It's again the same machine, the same die. We keep the same piston diameter. We increase the short sleeve length, so which means that one needs to, of course, manage with the fill ratio. And over here, suddenly the amount of gas which needs to be evacuated completely changes. So which is 5.8 liter or plus 71% compared to the case one. And then we go to the third one. So we modify the piston diameter over here, keep the same short sleeve length as the second one. Over here, there is a certain decrease in the gas which needs to be evacuated. So, but when we compare to the plus one, it is still above. So it's about plus 44%. So what does this mean is that there is a large difference in the gas that needs to be evacuated. And one way to do this is to really manage the venting well. The other way to do this is of course a vacuum system, which is going to help reduce this counter pressure influence. So here is an example of the vacuum systems that can be beneficial. So here what you see on your left is in fact a standard vacuum, so which is about, let's say, 268 millibar. And over here there are some residual gas inside the part. So this is basically an air entrainment, which can lead to get gas porosity. And what you see is about 40.7 milligrams, which stay as a residue over here. But on the same system, everything is the same kind of gating system and everything. So if we have a very high vacuum, if we are able to achieve a higher vacuum, so then the residual air is going to reduce it's to about 2.1 milligram. So one can just imagine what would be the residual gas for the same system with the conventional vents, which is obviously going to be higher than 40.7. So there are different ways to manage this. So one way is definitely vacuum, which is also becoming quite popular nowadays. So now we also move to the other aspect of the counter pressure. In fact, the counter pressure also has an influence on the die casting machine itself. Okay, and hence the injection process. To achieve this in the simulation, the machine data and the simulation parameters need to be linked. With an access to the machine database, which is the case now in Procast, one is able to select the right virtual die casting machine and hence predict the machine performance. This is what you see over here by means of this PQ square diagram. So basically the PQ square diagram is going to plot us the operating zone and of course also the operating point to notice where we are inside this operating zone. This can be translated to the Procast solver, and there is now an integration available between DCM and Procast. So thanks to this, in fact, the pressure request, if it is going to exceed beyond the maximum power available on the machine, the piston is going to get slowed down. So this is what you see over here. So this is the piston velocity profile of the piston. So we see over here that there is a slight change simply because the pressure is increasing beyond the maximum power available on the machine, and after a certain time the velocity or the plunger is dropping down its speed exactly like how it is on the machine, so which is nothing but a real-time piston control, just to be able to achieve a very precise injection sequence during the simulation. So this was also recognized as an innovation, and we were awarded together with our partners Ecotre and Colosio at the last METF. So finally, this does promote the Foundry 4.0, enabling the die casting machine and the simulation software communicate between each other. So as an example of this success is this case over here, what you will see on the slide. So as to how this DCM virtualization could help in reality. So here is a case of an automotive oil pump from BMW, so which was produced by one of our customers FAR in Italy. So what you see over here is a good casting with a good gating system, with a good vacuum system, everything well done with a 560 ton machine. So it was important to increase the production rate because the orders were higher, which meant that the foundry also need to make competitive pricing. And usually when we talk about such aspects, the obvious thing is to increase the cavity, and that is what was done over here to increase the cavity over here from 1 to 2, and which meant that the standard calculations without choosing the simulation meant that it had to be done on a 1200 ton machine. However, because of the DCM virtualization, we were able to achieve the same on a 750 ton machine. So what did this finally mean is that that it was not required anymore to manufacture on a 1200 ton machine, but just 750 ton machine was enough. This was also impacting on the cost savings per part, which was about 28% compared to the single cavity one. And one main benefit which also gets unnoticed, in fact, is imagine the same part would have been manufactured on 1200 ton and compared with, let's say, 230 days per year on 3 shifts would have costed plus 165 kilo euro more than what it is today with 750 ton. So there is a substantial benefits of also looking at not just the casting or the die or the design, but also to go one step further to understand on which machine this will be cast, what is the environment of the machine, and how it is going to help us. So finally, as a reminder, so let's say for the filling, so we went through the filling aspects. The main quality dashboards, let's say, is the gas porosity or the oxides, and of course what we saw just before is the machine selection. So once we are at this stage, so this is the stage where one needs to start building the dies. So we need to understand what are the hotspots in the die, and then we need to go with the cooling system. So which is very important, simply because we need to align these die temperatures with reality, so that we have established a stabilized die, or an operating die temperature, which is what is there on the foundry, and then come up with or modify or improve the designs of the cooling heating line, the lubricant spray, cycle timing, all these things. So this aspect can also be done in. There are several things itself inside this one to improve or to be able to be very precise. I will show you a couple of them. So one is in fact the to improve the spraying or the blowing visualization. So this is what is done. What you see, what you visualize over here. So in fact the spray head or the blow head, as it is on different dies, as the head is moving in reality, can be virtualized, so that we are able to extract exactly that moment of heat from that part of the die. And this spray head, of course, the lubrication can be applied depending on it depends on the spray head, the shape, the position, and also the release of the agent. So all these can be modeled. So one other aspect is the cooling lines itself. So the cooling line is a very important part of the die design, which is extracting maximum heat out of the die. So what is important is to also consider that there is a cooling media which is happening, just like metal inside the cavity. So there is a cooling media inside these cooling channels. So it's important to model this realistic flow of the cooling media, and this is now possible to achieve in Procast. And the benefit of this is also that it automatically computes the heat exchange of the die, and in fact this is in a function of the flow depending on its location and time. So one just needs to input your flow rate and your temperature, and that's it. So this means that Procast will have the unique possibility to actually model both. So which is, we are able to model the filling inside the cavity as well as the cooling lines, flow inside the cooling lines. So finally, the end of this complete full die validation is, of course, to understand what is also the stage with the porosity. So the porosity is only able to we are only able to achieve such a porosity with such precise die temperatures, and this can really help to predict the accurate shrinkage porosity. And we should also not forget that in die castings, the shrinkage porosity is not driven by gravity, and in fact it's driven by the intensification phase, where the plunger is holding up against the part. So the goal is not only to predict the locations of this porosity, but to also accurately measure these porosity and compare with the possible measurements which are available today in the industry, which is with these tomography machines, where they are able to compute exactly what is the size of the porosity, and if required, to also export this porosity, let's say, into the CAD, to understand what is the implication of machining post casting. And finally, as all these things are happening, so there is also one aspect which the casting is continuously being subjected into, which are in fact the thermally induced stresses. And for this, what is quite important is, because there is a shrinkage which is evident, but there is also a certain distortion, and because of this distortion, we can have different kinds of gaps between the casting and the die, or some regions which will have very very high contact. And depending on this gap width, or depending on this contact, what is also possible inside Procast is to be able to automatically adjust this interface heat transfer coefficient, to be able to have very precise cooling rates. And there are several aspects from, let's say, the residual stressors. One is able to predict let's say, the hot tears or cracks. And one main important thing which is happening, because all these parts are very thin-walled parts, these are going and fitting into another sub-assembly or assembly. So it is the dimension control. So one is required to achieve these dimension control, and the dimension control can be achieved in several ways. That itself is a topic. But what we are showing over here is an idea to integrate together with the GOM system. The GOM system, let's say, or these 3D scanners are quite standard in the industry. So these as cast parts are measured from these scanners, and there is also software which is provided, which takes into these points and forms this part. So we are able to export from procast residual stress output these distortion into this one, superimpose, and finally understand what are the deviations. So this is more simpler to analyze the distortions now. This is exactly like how our customers are used to do, and this is what we would like to bring it to you. So finally, as a performance dashboard, so residual stresses are quite important because it is affecting the dimensional control, and also it is affecting the as-cast properties. So this is also quite important. And we were so far talking about more focused, let's say, on the stresses in the casting, but at the same time there are also stresses in the dies. The dies are also continuously subjected to this one, which is in fact determining the tool life or the die life. And this is also possible to know from simulation as to how long my die is going to be well, so that I'm able to get good castings out of it. So these were, let's say the benefits in a summary of what is possible today in die castings. And what is one other important part is in fact the user environment to access these benefits. So what we have is we call it as a foundry oriented workflows. So it is based on each application. So we have gravity die casting, let's say low pressure die casting, high pressure die casting, the more standard ones. These can be customized, of course, to the needs of each industry. So what it basically does is it allows the users to choose as to what they would like to do. So they would like to fill, they would like to certify, would they like to do some cycling, microstructure, stress. You can choose what you want, and based on what is chosen, it is going to give you a kind of guideline as to what should be the next step, which is to be followed. So this is quite useful, let's say, for an entry level user, because then the requirement of the training is quite less. But this is also useful in case of automating things. So one can create automated tasks, or one can reduce the number of tasks which are done for every project. So let's say there is a certain task which is done for every project. So if this is going into the automated layer, so then you avoid doing such a thing. So basically you reduce each time, you learn more and try to figure how this to be automated. Of course, ESI is more than willing to help you on this one, to reduce the amount of time which is required for these setups and focus more on the analysis. So summarizing what we went through today. So we basically went through this entire die casting chain. So we started with the manufacturability checkup. So we went through the injection system design, and finally the die design and the process validation. So these benefits, these were let's say the peak of the benefits which I tried to put together. Though what is also true, when I try to put together, I try to make them somehow independent of each other. But what is also true is there is always a certain overlap between different benefits of this one. So one while designing, so it is quite possible that we would like to look into another aspect. So this is certainly possible, or to have one's own kind of a guideline. But this is a more like a generic guideline which could help to give a good start and to separate out the problems and to focus on only few aspects, to be able to realize the benefits of simulation. So as the die casting simulation always looks a complex thing with a lot of factors which are affecting each other. So finally, ESI Procast, it acts as a virtual assurance against any unforeseen tryout or production costs. So this is the whole purpose, to enable our customers to know all these unforeseen problems much before, so that one can innovate and cast with confidence to deliver premier quality castings. So we are not very far away from GIFA. So GIFA is, as you all know, is once in 4 years. It's less than 2.5 months from now. So we will be as usual on Hall 11. So this time the booth is H39. So if you are there, so please do meet us at GIFA. It doesn't mean that you don't need to discuss. We should not discuss for the next 2.5 months. So there is always a possibility to discuss in this time. So you could register. Let's say you're coming to GIFA, you could register on this link to already get contacted by us or to already get in discussion with us. So I mean that's it from my side for today.